Now we're going to talk about cache capacity. In particular, what happens when you run out of space in the cache? So what do we do when we run out of space? Well, we have to have a replacement policy. That is, we have to decide what do we throw out of the cache. So when we choose data to throw out of the cache, we evict the data. So we take the data and we move it out of the cache. We want to choose data that isn't going to be used soon. If we kick data out of the cache that we're about to use, it's going to hurt performance. So there's several approaches for this. So for a direct mapped cache, well, there's only one thing we can evict because every address can only go into one location. But for set or fully associative caches, we have some flexibility. And the two main ways to do this are choosing a random block to evict or choosing the least recently used, or LRU, block to evict. So let's take a look at the two of these. So here's random replacement. So we're going to pick a block at random to evict. We have a program here, and this program consists of two loops, a black loop at the top and a blue loop at the bottom. What we ideally want to have happen is when we switch from the black loop to the blue loop, we want all of the blue loop to stay in the cache while we're executing it. Let's see what happens with a random replacement cache. So we execute our first instruction, put it in the cache, our second instruction, put it in the cache, our third instruction, put it in the cache, fourth instruction, put it in the cache. Now we've got all of the black loop in the cache, and as we go back through the black loop, we have no problems because it's all in the cache. We keep going around, and then eventually we're going to exit the black loop. So at this point, we're going to exit the black loop, and we're going to go into the blue loop, and we need to figure out where to put the data in the cache. So it's a random replacement cache, so we're going to randomly choose a block to replace. So we go into our first instruction from the blue loop, and we randomly replace one of the instructions from the black loop. We go through, we randomly replace another one. Now at this point, we have two instructions from the blue loop and two instructions from the black loop in our cache. When we randomly choose another one to replace, this means we have a 50% chance of evicting an instruction from the blue loop. That wouldn't be good because we're in the blue loop. We want to keep those instructions in the cache. So we go ahead and do our next instruction, and we got lucky. We didn't evict a blue instruction. But now we have a 75% chance of evicting an instruction from the blue loop. When we go on to our next instruction, now we did that. So we just evicted one of the instructions from our blue loop because we chose it at random. And now when we go to do our next instruction in our loop, we have a 75% chance we're going to evict another one from the blue loop. So now we go up and we do the add I, and well, we end up evicting another blue instruction. So this is not good for performance. When you have a random replacement cache where you're randomly choosing things to replace, you may evict the data you're about to reuse because it's evicted at random. So let's compare this to least recently used, or LRU. So here we're going to pick the least recently used block to replace. So we've got the same example with a black loop and a blue loop. And remember, when we switch to the blue loop, we really want to keep all of the blue loop's instructions in the cache so it will run quickly. So we go ahead and start executing, and the beginning of the execution is just the same. We go through the black loop, we load all of its instructions into the cache, and once they're in the cache, we can go through the loop quickly because all of the instructions are in the cache. Now when we finish the loop and we go down to the blue loop, now we're going to have new instructions and we need to find a place to put them in the cache. But this is a least recently used replacement policy, so we're going to choose the oldest piece of data in the cache, which is the add. So now we're going to replace the add with our new blue add I. Now on the next instruction, now we need to find the next oldest piece of data, which is the jump from the black loop. Replace that, and so forth. We keep finding the oldest pieces of data in the cache to replace, and we replace them. So now as a result of this, we've got exactly what we want. We've got just the blue loop in the cache. And the reason this works so well is because of something called temporal locality. That is, if we just use data, we're likely to use it again. So LRU replacement tries to get rid of old data, the idea being that new data is more likely to be used. This is called temporal locality. So let's review the replacement policies. So we said that programs have lots of temporal locality. So that it's very likely if you just used something, you're going to use it again. We saw that in the loop. Random replacement ignores temporal locality, and LRU, or least recently used, is exactly a temporal locality policy. So in random replacement, you're just as likely to remove something new as something old because you're choosing it at random. But in LRU, you're always replacing the oldest thing. So you always keep the newest thing. So LRU sounds great. And in general, it is very good. And of course, anything that's in general very good has some sort of problems. And the problems are it's hard to build. So if you wanted to build a real LRU cache, you'd have to keep track of exactly in what order every entry was put into the cache. And this is very hard to do. If you only have a two-way cache, well, then you just need one bit to keep track of which is the oldest. But if you have higher associativity than that, you need lots of bits and it's very complex. So what people do in general is they build pseudo-LRU caches. These are caches that are kind of LRU and are generally close enough for most purposes, but are a lot easier to build.